Hey guys, this is Mr. Sal. We're going to look at rate of change, which is part of Unit 3, Lesson 6. Thanks for watching. Don't forget to like and subscribe, and comment what you think about the lesson below. Here's the great news about rate of change, is that it's a different word for slope. You may be wondering why in math we use so many different ways to say the same thing. It's to make us feel smarter than we actually are. Okay? I mean, just think about it, right? Like, as soon as people start to understand slope, then we change the dialogue into rate of change, and no one knows what the heck we're talking about, when in actuality, we know we're talking about the same thing, which makes us look smarter than we are, okay? That's not to be mean, it's just like an ego trip, I guess. Not that I ever think slope or rate of change will come up in a daily conversation for you guys. All right, so rate of change, yeah, it will be mostly in terms of word problems, though. But I think these are, well, at least hopefully they're slightly applicable for us. For example, if you drive 288 miles and use 9 gallons of gas, what is your rate of gas consumption? Now, you've only got two ways to calculate this, all right? You can either take the miles and divide it by the gallons, or you can take the gallons and divide it by the miles, and only one of these, kind of, will make any sense at all, okay? Here's what I mean. So if I did miles divided by gallons, I would have 288 miles, and divided by 9 gallons, which I believe is 32. Now you guys have seen this, and I don't care if you label it this way, miles per gallon. If you keep it as a fraction, that's fine as well. All I did is plug this into my calculator, or would have, and it should give me the answer at 32 miles per gallon. On the other hand, if I did 9 gallons for 288 miles, and I put this into my calculator, all right, and that would be gallons per mile. I don't know of anyone that refers to GPM, maybe GPS, but GPM is not the thing, so it actually wouldn't make sense really. Let me take that back. In rare cases, it would make sense to calculate how many gallons per mile, but for the most part, and hopefully just by life experience, we know that it would be miles per gallon, all right? Now again, even if we didn't recognize that, hopefully we understand that the whole value is easier to work with than that ugly decimal, which I actually assume kind of goes on even more than that on the calculator. I could be wrong. Last week you worked 38 hours and earned $479.94. What is your hourly pay rate? Now, instead of just calculating these as well, especially when we deal with money, which we could deal with decimals, like we did on that last one. And decimals on this case aren't necessarily a bad thing because of the cents kind of thing. However, it did ask specifically for the hourly pay rate, which means we want to know how many dollars you earn for every 1 hour. That would tell us the hourly pay rate. I'm not even sure how that would be worded for the hours per dollar. Maybe the dollarly rate. I don't know. In any case, we know that it sets up this way. So I'm comparing dollars in the numerator compared to hours in the denominator. And the values they gave us was $479.94 for every 38 hours worked. Some of you guys see we've created a proportion with this. However, there's no need to use it. Because we're looking for the hourly rate, we're just going to divide 479.94 by 38. All right, so up in this one, this would be $12.63 for every 1 hour. So I have it written like this just because kind of had it started like that. If you write $12.63, on the test you'd lose a point. Okay? And here's why, is because we want a rate. A rate will always compare two things, just like slope does with vertical and horizontal changes. So we do need to write in this that it's $12.63 Some of you guys like to write this out as per hour. I'm not even motivated enough to write the whole word hour, so I'm just going to leave it like this. But if you wanted to, you could. The following chart shows living wage jobs in Rochester per 1,000 working age adults over a 5-year period. What is the average rate of change in the number of living wage jobs from 1997 to 1999? And then we got the second one, which we'll get to here in a moment. Now, they gave us a lot of information on this. However, we're only looking between these 2 years, 1997 and 1999. So I'm just going to kind of box these in just to identify them. So we want the average rate of change in the number of living wage jobs. So for this one, we're looking at jobs per year. Now, again, it wouldn't really make sense to do this in years per job. Again, hopefully that makes sense foundationally, all right? Now, I'm not saying it doesn't have its uses, it just doesn't make a lot of sense, especially in a situation like this, okay? So, what are we going to do? Well, I'm going to set up because you guys like the formula for this, right? Y1 minus Y2, and it doesn't matter which one is which, but we do have to be careful with which one goes where. Now we know that the answer needs to be in terms of jobs per year. And the reason I set this up like this is to show that in the denominator is going to be the years, and the numerator will be the number of jobs. Okay, so again, it doesn't matter which year or jobs I start with, just as long as they correspond. So the jobs, I'm going to start with 1999 first. In 1999, there were 740 jobs. And then in 1997, which is the second year that I'm looking at, there were 620 jobs. So let's go ahead and simplify this stuff. So I'm going to calculate this. 740 minus 620, that's 120 divided by 2. So that's 60. Again, that goes to 60 jobs for every 1 year. Now, you may wonder if that was actually the case for 1998. The answer, of course, is no. But we weren't concerned with 1998. Just in terms of prediction, though, we would have anticipated there being 680 jobs in that case, not 690. So it kind of exceeded and then disappointed after that next year, but whatever. This next one is going to work the same way, except for this time we're looking at 1999 again, and then to 2001. So I'm going to start with 2001 in this case. So in 2001, there were 810 jobs. And then in 1999, once again, there were 740 jobs. So I'm just calculating this. Again, it's in jobs per year. 810 minus 740 is 70. And 2001 minus 1999 is 2. So it was 70 jobs in 2 years, which would simplify to be 35 jobs on average every 1 year. Now, whether that average is actually true or not is not important, just that we know that on average we would expect 35 jobs per year change. Now, these two are very different, and that's because, especially when we look at statistical data like this, it's never really consistent. Just depends on how you want to compare it, and if you, what the purpose is for the data. So if I wanted to, right, because politicians do this all the time, if I was saying, man, we want to show how many jobs we created in Rochester, then I would use 1997 and 1999, right? In comparison to 99 to 2001, because on average it had a higher number of jobs per year, and voters, whether they know it or not, like it when you show higher numbers like that, even if it sometimes is a bad thing. A city's population in the year 1947 was a lot of people. In 1998, the population was a little bit more. By the way, this is the problem that the reality check is going to look like, unless they've changed it. What was the average rate of change? Okay. So, just like at that last problem, this one's going to work the same way, except the difference is that it's not in a table. All right. Now we're looking at rate of change. The two that would make the most sense, the one that would make the most sense, would be population or people for every 1 year specifically. So this just helps me figure out where I'm going to put my X and Y values or the population in years. So starting with 1998, there was a population of, a lot of population. Sorry, I didn't have enough space for that full number. And then in 1947, the year, there was 2,860,700. So we are subtracting these, and this will tell us the population change over, looks like 51 years. 17,500 people over the 51 years. So how many people is that for every 1 year? That simplifies to 343, maybe 0.3 repeating or something like that. In any case, and I do believe it does say that on the homework, to round to the nearest person, which would be, in this case, it appears, 3. So the average rate of change, 343 people per year. Determine the rate of change from this graph, but again, it really is just asking what the slope is. So, again, if I'm remembering right, when you see this on the homework, it's the same answer, because slope is the rate of change. So on this, we're going to find 2 points that we can positively identify, like this one. Now be careful, the scale on the x-axis is kind of jacked up, all right? So this point is at negative 60, and the y value is 5. And another point I can use, there's several, but I'm going to use this one, not to be a jerk, but just to show differences, all right? Because some of you guys see the 2 intercepts, and that'd be fine as well. In any case, this value, it doesn't show that y value on the x value on the number line, but we know that the scales have to be consistent. So it goes from 20, it has a line, then it goes to 40, which means this line has to represent 30. The y value here at the bottom here is negative 10. Now you could use a stair step, you could use the formula, you could use the rainbow method, whichever one you choose. Since it's already on a graph for me, I'm going to use a stair step. So from 5, it went all the way down to negative 10. That means it went down 15. I mean, I could count the lines, but we got to be careful again when the scales are kind of different. And then we went from negative 60 to 30. That means I went in the positive direction, 90. So my slope will be negative 15. Sorry, also the rate of change. Negative 15 over 90, which does simplify. This is both simplifiable by 15, which your calculator will do for you as well. So that'd be negative 1 over, so that is the rate of change, negative 1/6. And again, it doesn't matter where that negative is. So the slope is the same, negative 1/6. Again, rate of change and slope are exactly the same thing. Now this one, this has, I guess they didn't really emphasize the axis on this. This is the x-axis right here and the y-axis right here. This one's a really good one, again, because we need to understand that scales will depend on the values that we have. So we got to be careful on this. Each line on the y-axis, for example, is representing 400 each. And then on the x-axis, though it doesn't show these values, it's going up by 20, each of those lines. So, but the process is still the same. If we can just identify 2 points, Well, these two are pretty close to each other. And again, it doesn't matter if you choose these two or any other two, you should get the same slope. Let's just identify the coordinates here. Last time we used a stair step, so we'll do this one a little different. You guys like the formula for this thing. So I'm going to say that this is my first point here at 3600 for my y value, and my x value is 20. Again, it doesn't matter which is which. And then this can be my second value, second point, at 3200. And the x value is 40. So solving these, 3600 minus 3200 is 400. And 20 minus 40 is negative 20. Just to fully simplify that, oh, sorry, the zeros cancel, so it's going to be a whole value on this thing. Negative 20. There it is. Now, it did ask for the rate of change. There's no labels on this. Otherwise, it would always be the y, whatever the y label is, divided by the x label, because it's always the y's divided by the x's for slope or rate of change.